Okay, so we are returning for a coffee break with the first tutorial of this workshop. It's going to be presented by Professor Rodrigo Caiado Delamar from the Pontificio Catholic University of Rio de Janeiro. Professor Rodrigo received his degree in electronics engineering from the Federal University of Rio de Janeiro in 1998, and his master and PhD degrees in electrical engineering from PUC-Rio in 2001 and 2004. Since 2006, he has been a professor at the University of York in UK, and since 2013, he has also served as professor at PUC-Rio. Dr. Delamar is a senior member of the IEEE, and he has contributed as an editor for the IEEE Wireless Communication Letters and IEEE Transaction Communications. He currently serves as associate editor for the IEEE Transaction Signal Processing. His research focuses on communication signal processing, and he has authored more than 600 papers in international journals and conferences. His talk is about interference cancellation for self-free networks with multiple antennas. Professor Rodrigo, the floor is yours.
Thank you. Thank you very much for the invitation. Let me position myself here, the right spot, okay? Thank you again for the invitation. Is the audio okay for all of you? Okay, so this work was done in collaboration with my former PhD student, Tony Setumba, who is now an assistant professor back in Uganda. He's from Uganda. So my current postdoc, Said Manshdur, and my colleague, Lucas Landau. This is also part of a collaboration with CPQD, an industrial PhD, two industrial PhD students that we had. So Tony and Said. So this was work done in collaboration. And I'm with the Center for Telecommunication Studies, the CETUC, which is now part of the Department of Electrical Engineering at PUC-Rio, and also with the School of Physics, Engineering, and Technology at the University of York. We are based here in Rio de Janeiro. Okay, I'm based here most of the time, 11 months a year, and 1 month a year at York in the UK. And so I'm going to give an outline of the talk now. So I'm going to start with some introduction, why we're doing this. And then I'm going to explain the system model of a clustered self-free multiple antenna system. So this is a topic that has been gaining a lot of interest recently because of the potential to improve coverage and improve data rates for 6G systems. Then I'm going to describe the channel and the interference estimation strategies that we developed for this work. And then I'm going to detail the proposed iterative intra-cluster and out-of-cluster interference cancellation. These are two types of interference that occurs in this type of network, and they are quite interesting to kind of for us, because this is going to be probably prevailing in future systems. We're going to see interference that is inside a cluster that is serving, say, users and has access points. And we're going to also have out of cell or out of cluster interference coming from other systems, other networks, such as satellite networks or nearby networks and so on. And then I'm going to illustrate the ideas we developed with some numerical results. And then I'm going to wrap up with some conclusions and ongoing work that we have in our research group. Okay. So self-free multiple antenna systems deploy a large number of distributed access points in the coverage area and processing with a CPU. So the CPU is used to get the data that we have in a cluster, and they do the processing. For example, they compute the receive filters, they compute the LLRs, they perform decoding, and so on. Okay. So AP clustering techniques have been proposed because these systems that you have distributed antennas, they can be quite challenging in terms of the amount of signaling that is required. What is this signaling? It's the amount of information that you have to carry using the network to, for example, to coordinate transmissions, to tell which users are active or not, and etc., and what access points should do. So all this coordination is done via signaling. And if you want to do a distributed network that all APs and all users communicate with each other, this is, of course, impossible to do. It's not practical because the amount of signaling very quickly goes up. So we have to come up with something to make it what we call scalable. Okay, this network should be scalable. We should be able to do this in a scalable and effective way. So the answer to that is the use of AP clustering, or clustering in general. Okay, and for clustering, we can use a number of different approaches. We can go back to machine learning, for example, to information theory with vector quantization, and the way that we create code books, for example, using k-means, LBD algorithms for vector quantization. They are the basis for clustering, okay, that we use in machine learning. And they can also be applied to these networks. However, one of the problems that we are dealing here is not only the clustering, is the interference that occurs not only inside each cluster, which we call intra-cluster interference, or ICL here. We also have out-of-cluster interference coming from outside, okay? Because we are limiting the number of APs and users that are communicate with each other in the cluster for the reason of scalability. So we also need to do now with this interference that comes is outside, okay? And this can be quite damaging for the communication. So in this work, we study ways of mitigating this intra-cluster and out-of-cluster interference, and how we can do this in an effective way and in kind of efficient as well. Okay. So key problems that we identified in this study is that ICL and OCL interference mitigation requires channel and interference estimation. When I say channel, is the channel of the intra-cluster users. Of course, we want to estimate their channels because we want to decode them. But we also want to obtain some estimates of not exactly the channels that are outside the cluster, but of the interference itself. Because if we have the interference, we can model it, we can estimate it, and then we can try to subtract it from the received signals, okay? And that's the idea of the work. And this is the key problem that we are dealing with, okay? And then, of course, we're going to try to design high-performance cluster-based receivers. Specifically, the OCL estimation, this out-of-cluster interference estimation, needs specific modeling, pilots and estimators, which is challenging. I'm going to show you why this is challenging, and then I'm going to basically describe all the steps that we need to do that. Okay. So basically, our contributions is to propose an iterative soft intra-cluster and out-of-cluster interference cancellation scheme for the uplink of these user-centric clustered multiple antenna networks. We're going to show how to model the out-of-cluster interference, and we're going to devise a least squares estimator to perform out-of-cluster interference estimation. Okay, this least squares estimator is a very basic least squares estimator. Okay, of course, people can come up with improved estimators, and this is kind of open in the field. Okay, we also devised an MMSC receive filter with a novel parallel interference cancellation scheme for the receiver to mitigate both intra-cluster and out-of-cluster interference. So here, the parallel interference cancellation builds on prior work on parallel interference cancellation in the context of spread spectrum systems, MIMO systems, and so on. But we add extra terms, okay, in the subtraction, in order to be able to mitigate both intra-cluster and out-of-cluster interference. And then finally, we devise an iterative detection and decoding scheme that adopts LDPC codes and incorporates the intra-cluster and the out-of-cluster interference estimates. Okay. So let's start with the system model that we are interested here. We consider the uplink of user-centric, clustered, cell-free, multiple antenna system with L access points that I call APs, each with N antennas. Okay, so each AP is equipped with N antennas. Okay, why is that? Because if you have multiple antennas at the each AP, you have also array gain. So this is an advantage. So this is a trend. So we don't use APs with a single antenna anymore. Okay, we consider M out-of-cluster interfering signals and K single antenna users that originate intra-cluster interference. Okay, so if we don't consider their out-of-cluster interference signals, this would be a pretty conventional user-centric cell-free system. Okay, but in our case, we also have the out-of-cluster interference. Okay, and at each receiver, the receivers are based at the, let's say, at the access points. The access points would be the receiving end, but the computation of all these tasks here, the detection, MMSE receive filter, decoding, and all these tasks that we expect from a receiver are done at the CPU level. Okay, so these access points that we have here in the clusters, they are connected to the CPUs. Okay, so the CPUs will do the computation, and we are equipping these, let's say, these receivers here with an IDD scheme that you can exchange software information, and we also have LDPC codes. Okay, and the goal of our work is to mitigate this intra-cluster and out-of-cluster interference. Okay, and then of course decode the transmitted symbols. Of course, this requires the estimation of both intra-cluster and out-of-cluster interference. So this is basically the same. What we are going to do in the computations here is to transform the received data by each access point here. Okay, we're going to transform them into LLRs because they are sufficient statistics. And we're going to use the LLRs to exchange the information, okay, between the decoder and the receive filters iteratively, as we call them. Okay, we're going to do multiple passes between the receiver and the decoder. Now, so the received signal, mathematically speaking, at each AP, after estimation of the channels of the UEs and the out-of-cluster interference, is given by this equation that we have here. So this is we assume that each AP has n antennas. So this is an n-dimensional receive vector, okay, that is obtained by matched filtering and obtaining sufficient statistics, okay. And this HL is the channel of the intra-cluster users, and X is the data from the users in the cluster. Okay, GL is this is the matrix that models the channels of the out-of-cluster interference. Okay, and S this is the symbol vector of the interference outside the cluster. Okay, or the users outside the cluster, and of course NL is the noise. Okay, at the receiver. Okay, and this happens for each AP, okay? And of course, we have multiple APs, and we're going to work with them together. We're going to stack all this information of the APs, and we're going to send this information that is tagged to the CPUs, and the CPUs will perform all those tags for receive processing, decoding, and iterative processing, okay? So that's our strategy. But of course, as I mentioned before, we need to estimate the channels, both the intra-cluster and the out-of-cluster channels. So let's go to this task of channel and interference estimation. So in order to estimate the channels, we need to have K mutually orthogonal tau p greater than K length pilot signals. So we need at least K pilot signals, okay, to obtain the channels of the intra-cluster users, because we have K users there, okay. And sorry. So the received signal during the pilot phase, so we have at the receiver, we have a pilot phase, and we want to estimate the channels. And so this is the received signal that we have after collecting the data for tau p snapshots. We're gonna get this, which is a matrix. And here, this is the matrix with the pilot symbols, okay, for the intra-cluster users, and these are the channels. So at this point here, we are only interested in estimating the intra-cluster channels. So we're gonna use the least squares estimation, which is a very simple estimator to obtain estimates of the channels of the intra-cluster users, okay. So this is the first step, okay. We obtain the channels of the intra-cluster users. Then, in order to estimate the auto-cluster interference, okay, or simply the auto-cluster channels, the received signal at each AP is first processed to reduce the impact of the channel of the serving UEs. So this is something unconventional, okay. What we do here is some interference subtraction. So all the contributions of the intra-cluster users and the pilots here are removed from the received signal, okay? And then we get this residual signal Z sub L for each AP. After some mathematical manipulations, this equation here can be rewritten as this other equation here. And what we have here outside, okay, is simply a projection matrix, okay, P, that is a projection onto the orthogonal component of the pilot matrix, okay? So it's like something different. It's orthogonal to the pilots that were used for the intra-cluster users. So we are now interested in something else, which is the out-of-cluster interference. So this processing is important for removing the part of the intra-cluster users, which is the channels of them, and focusing on the out-of-cluster interference, okay? So this projection matrix here is not invertible. So the out-of-cluster interference cannot be completely estimated. This is very important. But we don't need to completely estimate them. We need at least a coarse estimate of the out-of-cluster interference that is good enough to remove it, to subtract it, and kind of clean the signals that are observed by the APs of each cluster, okay? So what this means that also that only the components spanned by the projection matrix can be estimated. So this projection matrix, we have to be careful with the number of pilots. This suggests that we have to increase the number of pilots, okay, so that we have more components spanned by the projection matrix. So this indicates that, so we increase the number of pilots from K to K plus M, and M is the number of out-of-cluster interference signals that we want to estimate, okay? So this is done on purpose. So this projection matrix can also be decomposed or written in another way. So we can write it in a slightly different way, and these psi matrices are a bit different. They have dimensions tau p by tau p minus k, and they satisfy this orthogonality property, which yields the economy size singular value decomposition. Okay, so at this point we can state that to estimate and mitigate intercluster and out-of-cluster interference, we need the number of pilots that should be k plus m, okay, or tau p greater or equal to k plus m, because we need this for the intracluster users, and m for the out-of-cluster interfering signals, okay? So this is pretty clear that we need some extra pilots for that. And the excess number of antennas in the cluster APs also needs to be sufficient to allow the components spanned by the projection matrix to be estimated. What does it mean? It means that we are working with a cell-free system with many access points, and the number of access points and the number of antennas in total should be sufficiently good or sufficiently large to allow this excess number of antennas to have the massive MIMO effect for interference mitigation, and also to have an excess number of antennas to allow this projection matrix to be estimated. So we are using massive MIMO, the massive MIMO concept, with this excess number of antennas to allow for this projection matrix to estimate our out-of-cluster interference. This is also fundamental for us, okay? So then the projected signal component will be the following. We're going to use this basis here of the projection matrix to project our matrix with the data of the out-of-cluster interfering signals, okay? So we project them, and then we compute this residual signal, which is this spread by projecting it on this basis as follows, with this equation here. So ZL that we had before, which was ZL was this residual signal, okay? We removed the components of the intracluster users. We use them with this basis of the projection matrix to obtain this, okay? And then what happens is, with the knowledge of this basis here and this Z matrix, we can form a sequential accumulation of Gramians. All of you have taken linear algebra here. Probably you don't use it for breakfast like every day, like myself and my students who are working on this. But the Gramian is like a quadratic form of this type. We can accumulate the Gramians obtained by each AP, okay? And we use this accumulation of Gramians followed by the computation of the estimates of the data of the out-of-cluster interfering signals, which is this S bar hat, and the channels of the out-of-cluster interfering signals, okay? So with this accumulation of Gramians, we can cast a least squares problem like this one and obtain the estimates of G and S, which basically form the out-of-cluster interference, okay? This has a cost that is proportional to K, number of users, times N, the number of antennas at each AP, times L, okay, the number of APs, okay. So solving this allows us to obtain the out-of-cluster interference, okay. Now we are ready. Now we can estimate the channels of the intracluster users and the out-of-cluster interference. We can now describe the proposed iterative ICL and OCL interference cancellation. So what we are going to do is to write the received signal at each AP here in the form of this, that you have the intracluster channels and the out-of-cluster channels, and the data from the users inside the cluster and outside the cluster, of course. So we are writing this received signal in this way, and then we can, for centralized processing, we can stack together the data from all the APs, okay, in a very big vector here, and then we can process this received data vector, this large vector, with the data from all the APs, and we can, at the CPU, we can perform interference cancellation here. In this form, we have the desired signals, okay, here the interference and some noise, okay. And what we do here is the following. When we write the data like this, explicitly we are showing the desired signal, that would be one particular stream of data, okay, and we have all the other streams of data as interference. We have the capital K intra-cluster users and out-of-cluster interference, plus some noise. At this point, we are able to perform parallel interference cancellation to remove everything that we don't want, which is these components here, okay? So then the detected signal for the desired user would be something like this, okay? We perform some linear combination here of the receive filter with this receive data vector that is stacked at the CPU, okay? And then this is the form that we have. This is the MMSC filter that we derive by solving this optimization problem. And then this output that we have here, we employ a Gaussian approximation, because this is very effective to perform interference cancellation with iterative processing, exchanging LLRs, and this is very precise, okay? So we transform the data that we have into LLRs because they are sufficient statistics, and we're gonna exchange these LLRs between the receive filter and the decoder. We do this a few times until these LLRs are refined and we can make decisions about all the symbols, okay, with all the interference removed, okay. So now let me illustrate all this theory and all these algorithms to you with some examples, okay. We have a network set up here that we have a user-centric cell-free clusters with radius equal to 0.5 kilometers, okay. The channels between the out-of-cluster UEs or users and the APs are generated randomly. We use QPSK and 16-QAM modulation schemes. And we also use large-scale fading coefficients that are obtained by the 3GPP urban microcell model given by this equation here. So this is done because many papers use this model, okay? This model is not necessarily the very best that we have, okay? Now people are performing measurement campaigns for cell-free systems. And we're gonna have much better models, hopefully in the near future. And for the generation of these numerical results, we opted for a small system, okay, which is easier to simulate. So we use code word length of LDPC codes of 512. Of course, we can use much longer codes, and this is important to reduce the error rates. But in our case, we are keeping this to 512, the code word length. And that's also a half rate code because we have 256 message bits. We use tau p equal to 10 or 12 pilots, okay? Depending on the example I'm gonna show here. The maximum decoder iterations that we allow for the decoder, the LDPC decoder, is 10. And the IDD iterations, we use 3. Only 3 passes. Exchanges of LLRs between the receiver and the decoder are sufficient to clean up the signals from interference, okay? And we have scenarios with L equal to 32 access points, okay? They are spread in the clusters, okay? And we have 4 antennas per AP, or per access point. And we have 8 users, intra-cluster users, to be specific, k equal to 8. And we have either m equal to 2 or 4 out-of-cluster users, okay? So let me show you the first example here. We have, for these parameters, we are having here 4 out-of-cluster interferers, okay? I'm measuring the normalized mean squared error in dB versus the SNR, okay? For our channel estimator, which is very standard, is a least squares channel estimator. So we get this. We have in black, we have the interference estimation that is done before the channel estimation, and we have also the option to do the interference estimation after the channel estimation. So the black one is before channel estimation, and the red one is after channel estimation. We call them pre and post. So we opt for the red one because this is better, okay? But you can get improvements if you have more sophisticated estimators. We have only least squares estimators here just to make the idea simple, okay? And this is the scenario with 32 APs and n equal to 4 antennas per AP. So if you multiply L by n, you have 128 antenna elements to deal with 8 intra-cluster users and 4 out-of-cluster interferers, okay? So that's a massive MIMO setting, okay? Now, a second example, we show this set of parameters here with QPSK symbols, okay, and a varying number of iterations, okay, between the receive filter and the decoder. So what we have here is for one iteration, this is the error rate that we get. That's pretty bad. And after 2 and 3 iterations in blue, we get a better performance. So we are getting not far away from 10 to minus 3. Please note that these error rates are not good because the LDPC codes that we are using are very short. So it's 512 only, okay? But we can bring this down to 10 to minus 6, 10 to minus 7, just extending the LDPC codes to about 1500 of length, okay? So this is not a big deal. But the problem is the simulation. Simulation takes some time. So that's why we opted for a smaller system, okay? So this improvement of iterative processing is known, but in this context is kind of has some novelty, of course. As you can see, we clean the signal that we want from interference by doing this iterative processing, okay? And after 3 iterations, we don't get more benefits. So we can remove most of the interference here. And here is the BER performance versus the signal-to-noise ratio. This is a very interesting plot. I'm going to explore this a little bit more. Here we have, again, 32 APs, n equal to 4 antennas per AP, 8 users inside the cluster, and 2 out-of-cluster interferers. And we are using QPSK symbols here. The worst performance here, this is the red curve, is obtained by a linear receiver, which is unaware that we have out-of-cluster interferers, okay? But is suffering from it, okay? So this is the worst performance that we can get, okay? So it's not able to deal with this out-of-cluster interference. The very best that we obtain here is the black curve. The black curve is the parallel interference cancellation. So we remove all the interference, okay? And we don't have out-of-cluster interference on purpose here. So there's no issue to cancel this interference. So it's a clean cluster in terms of out-of-cluster interference. And we only have intra-cluster interference. So the parallel interference cancellation here does the best job possible. Okay, that's the black curve. Now, if we use a standard parallel interference cancellation or a linear interference linear receiver, which is in green, and this linear has no out-of-cluster interference, it doesn't perform so well here. You see? So it's in the middle, it's halfway from the worst to the best. Okay, and the proposed approach is the blue curve. The blue curve is this parallel interference cancellation that is modified to deal with both intra-cluster and out-of-cluster interference. Okay, so you get very close to a parallel interference cancellation that doesn't suffer from out-of-cluster interference. So this is very interesting because you're doing very well. So almost no interference here remaining. Okay, so this shows that we are able to cancel both intra-cluster and out-of-cluster interference. So now we have another scenario that is very similar, but now we were testing another concept that is kind of quite useful for modern networks, that when you are unable to acquire channel state information, for example, or some other parameters of interest, you can use statistical knowledge of it. Okay, some systems use that, and we call this statistical channel state information. We can use the statistical channel state information about the out-of-cluster interference as well. This is would be kind of natural to consider that. And using this, we get this green curve here. It's we lose a bit in terms of the whole system that is trying to estimate out-of-cluster interference, which is better, but we're still able, with the green curve, to do better than a parallel interference cancellation that cannot deal with the out-of-cluster interference. Okay, so this is another advantage we have here. And here's a similar result we have. BR against SNR for 16 QAM. Okay, 16 QAM, you can see that the performance gets worse. Okay, you need higher SNRs, and you need also, of course, more powerful codes, which we didn't use here. But the same hierarchy in performance is observed again. So we have this proposed idea of estimating both intra-cluster and out-of-cluster interference, and devising a detector that cancels both in blue, gets as close as possible to the optimal, okay, that we have in this context. So and we come to the conclusion of the talk. So we investigated soft interference cancellation schemes for user-centric clustered cell-free massive MIMO networks in the presence of intra-cluster and out-of-cluster interference. So we developed MMSE receive filters, proposed a modified peak receiver, and devised a least squares estimator to perform out-of-cluster interference estimation. An IDD scheme that adopts LDPC codes and incorporates this ICL and OCL interference estimates, and the modified peak receiver were also presented. And the results show that the proposed techniques, they outperform competing approaches, and they can get very close to a system that doesn't suffer from out-of-cluster interference. Okay, so in general, the iterative processing becomes more accurate with intra-cluster and out-of-cluster interference cancellation and the use of this modified, this improved peak receiver. So basically, we continue to work on this. So we are now looking at clustered cell-free designs with out-of-cluster interference for broadcast channels. So we're now working on the downlink, as we call it. Okay, So we can design precoders that can incorporate out-of-cluster interference, and they can do resource allocation with out-of-cluster interference knowledge. So you are aware of what's going on in terms of out-of-cluster interference. And we're also looking at extensions of this to multi-cell systems and comp, what we had in 4G, okay, and also we have in 5G dot, because this concept can be used for user-centric cell-free networks, but also for the traditional multi-cell networks. Okay, this is no issue with that. Okay, it's just an adaptation. So I think with this, this concludes my presentation. Okay, so I'm happy to answer questions.
We have time for questions. Okay.
Well, thanks, Professor, for the great talk. Well, I have two questions. One is related to the complexity of the proposed estimation process. You said that it was K times L times N times A, right? Because is the number of K orthogonal signals,
Right.
the number of pilots, the times the number of
let me
receiving antennas.
go to the slide. Yeah.
Yes, Chi times antenna. And so that is compared with the state-of-the-art estimation algorithms. That is high. That is relatively good enough.
It's in line. It's comparable.
It's comparable.
Yeah, because in this case, it's a rank 1 approximation. So what you do, you don't do the full SVD, the full single value decomposition. You can just do, a simpler version of that by, for example, some power iteration or something like that. So you can basically compute only the singular vectors that are of interest. Okay, you don't need to do the full SVD.
And the other question was related to the number of pilots that you need to compute this algorithm. Was K plus N, I think.
Yeah, here.
Plus M, yes. That M, I know K is from the orthogonal signals, so that's okay. But the plus M, where did it came from? Came from the inversion of the projection matrix, or from
yes,
where?
That's a good question. Okay, so this number of pilots, tau p, should always be greater. If you think about Massive MIMO, I think many of you might have seen Massive MIMO as in its inception, right? So if you consider Massive MIMO that you have like N antennas, and then you have K users with K single antenna users, to be specific, okay? So you only need capital K pilots, okay? But imagine now that in one cell, for example, of Massive MIMO, you have something coming from outside, just out of cluster interference, okay? And you have M interfering signals, M out of cluster interfering signals, to be specific. So what you need to be able to perform a coarse estimate of that is some extra pilots in the M, to be specific, okay? So you add that to your need for pilots, okay?
More questions? I do have one.
Yeah.
You mentioned that the performance of the system was not so good because you're using very short LDPC. We know that polar codes can perform better than LDPC if the code length is quite short. So have you considered using polar code instead of LDPC in this case?
That's a good question also. You might get a little bit better with polar codes, okay? So that can be used. So that's what was one suggestion from Tony's thesis, that you should do the same kind of exercise or examples with polar codes. We might get some improvement here in BRs. Okay, I don't have the the results for polar codes here, but I might have a few examples with longer LDPC codes. This is what I anticipated to you. So if you go to 1024, 1500, around that, you bring this to about 10 to minus 6, and then it's kind of a good enough for a network. Okay, but the point is good. With some polar codes, you might get some improvement, a few fractions of dB. Okay, but then we don't know if the polar code will go to 6G or not. And at the moment, also it's for control channels. So we are considering data here. So we thought it was more natural to consider LDPC codes. Okay.
And the last question, you mentioned that you sent the pilots and then you use them to perform the decoding, right? How fast do you need to update the pilots regarding the channel changes over time?
Okay, it's another good question. So what we are assuming here that the channel is static over a block or over a code word. Okay, so we are not considering tracking here. Okay, so every code word is only with one channel realization.
So it's block fading, basically.
It's a block fading. Okay, it changes every block, but is very well behaved. We don't have changes inside the block, so we don't need to track. So the tracking would be a more challenging problem, especially for the out of cluster interference. Okay.
So one question here.
Thank you.
This works.
Yes, it's on. Are you hearing me? Thank you for the presentation. I have a generic question. You were commenting that for simulation, you were doing an assumption to use a small number of iterations. So, but in a real deployment, a hypothetical real deployment, maybe we will require a huge number of iterations. Did you analyze the complexity from that point of view? That was one question. The other question was related to the question that Luciano made. It's about the mobility. In case the UE is to going to 30 kilometers per hour, if the user is going to 500 kilometers per hour, maybe the channel will be different. What could be the impact?
Yeah. Let me answer the second question first. Okay. That is a very good question, because this brings me to in terms of the network architecture that people are thinking about for 6G. So in the case of mobility, or mobility that is higher level of mobility, we're going to probably use a macro cell. Nobody's going to get rid of a macro cell in the future. So this architecture here, the cell-free, is more suitable for an area of high density, like a football stadium, a big city center, like a concert, something like that. So you have high density of users. Some people might require high data rates, and we're not thinking about a very high mobility. But if you go to a scenario of high mobility, probably you're going to hand over to a macro cell. Okay, and then we won't probably use this. Right. In terms of the first question, which was about the number of iterations and the complexity, etc. So as you can see, we could use more sophisticated receivers. We opted for interference cancellation that we know that has been used, like parallel interference cancellation, soft interference cancellation, successive ones. They are known. Okay, they have been used for decades in different generations of mobile systems. And so the complexity is comparable. Why? Because, let me show here in the equations. First thing is the iterative processing is similar. Okay, once you have the LLRs here, okay, exchanging, this is similar to what's done, okay, by other systems, okay. what changes for us is the following. This part here, the summation here, and the way that you subtract is different because you need more components in the subtraction. So you have M extra components associated with the out-of-cluster interference to subtract. And this costs a little bit more, okay? This is a cost that is, okay, maybe I would say 20% higher because you need to subtract, okay, this interference component. And we also have an extra cost. Beyond that, we have the extra cost of this interference estimation here. So we need another least squares problem that needs to be solved, which has this cost here to obtain an estimate of the out-of-cluster interference, okay? So it costs a bit more, but it has some benefits, okay? So you have to waive that, so people from industry should kind of test that, okay?
We do have time for one last question. If you don't have any more, you can thank Professor Rodrigo once again.
Thank you.
Thank you.